In this example problem, we'll be looking at the same section that we have been looking at for the previous example problems. This this square section, 18 by 18 inches with a given area of steel, area of pre-stressing, and area of concrete. What we'll do in this example is we will find the average stress caused by a 1/8 inch imposed deflection on the column, the axial force at that 1/8 inch, and then the local stresses at a crack caused by this 1/8 inch forced displacement. We're going to include the effects of tension stiffening in this problem. So that'll be the new component for this example. Some of the properties that we'll need the tensile strength of the concrete. And since we're in direct tension, we're going to use our 4 square root F prime C equation. And we can then find 4 times the square root of 7,000 psi divided by 1,000 pounds per kip gives us our tensile strength in direct tension for the concrete. We can find the strain in the concrete at the time of cracking by taking this tensile stress divided by the modulus, which is 4,770, giving us our cracking strain. Some of the other values that we'll need, we need to find the initial strains that occur during the tensioning process. This is a post-tensioned member, so so the concrete will deform as the post-tensioning is being applied. To do this, we need to find our modulus, we need to find the initial strain in our pre-stressing, and also the force in the pre-stressing after our post-tensioning. So I find those values here. We can use our equilibrium equation to find the deflections caused by our post-tensioning. And note our sign convention will be negative is compression and positive will be tension. Our equilibrium expression, internal components, concrete, steel, and pre-stressing equal our external applied load. At initial pre-stressing, we have no external applied load, so we just have our internal forces equal to 0. You can see we're going to assume linear elastic material properties, so our stress is just equal to our modulus times our strain. And then we can plug in all of our known values, and our only unknown value is the initial strain in our concrete. So solving for this, in this equation, we can find the initial strain in the concrete after post-tensioning to be negative 0.131 times 10 to the negative third. Our locked-in strain then for a post-tensioned column, we have equal to the initial strain in the pre-stressing minus the strain that's in the concrete after post-tensioning. Note that we have a compression strain in the concrete, so it'll be minus a minus, so we're adding the 0.131 times 10 to the negative third. That gives us our total locked-in strain after post-tensioning to be 6.27 times 10 to the negative third. Next, we can find the average stresses caused by the imposed displacement, including tension and stiffening effect. And the first thing that we need to do is we need to find our average strain. So our average strain is just our 1/8 inch, so 0.125 inches, divided by the overall length in our column. We have a 20-foot column times 12 inches per foot. Which will give us an initial strain here of 0.52 times 10 to the negative third. So this is greater than our cracking strain, which we found on the previous slide. So we know that our concrete is cracked. Because our concrete's cracked, and we're looking for the average response, we're going to include tension stiffening. So we'll include tension stiffening using the equation shown here, where we have a alpha 1 factor taking into account our bond characteristics, an alpha 2 factor taking into account whether we have long-term or short-term loading. We'll calculate our alpha 1 on the next slide because we have a combination of non-pre-stressed steel and pre-stressed steel. But our long-term loading will assume that we have short-term loading, so we'll have an alpha 2 of 1.0 for that. Because we have both pre-stressed and non-pre-stressed steel, we need to take a weighted average of of the pre-stressed versus the non-pre-stressed steel. So our alpha 1 factor is going to be equal to the area of our non-pre-stressed steel, 4 square inches, times 1.0, which is the alpha 1 factor for our regular deformed reinforcement, plus the area of our pre-stressed steel, times the alpha 1 factor for our pre-stressed steel, and then we divide that by our total area of both our pre-stressed and non-pre-stressed steel, 5.224 square inches. So we'll get this alpha 1 factor then to be 0.93. Our alpha 2, we're looking at short-term loading, so our alpha 2 is going to be equal to 1.0. And our average strain in the concrete is going to be equal to the strain in the column, because we're going to assume that we have no thermal and no shrinkage strains in our concrete. So now we can plug all of our known values into our tension stiffening equation. We'll have our alpha 1 of 0.93, our alpha 2 of 1.0, the tensile strength of concrete being 0.335 KSI, and then we'll divide by 1 plus the square root of 500 times 0.52 times 10 to the negative third. And all that's under the square root. So we'll find the average concrete stress then to be 0.206 KSI. The average steel stress we can find by taking the modulus of our steel times our strain in the column, 0.52 times 10 to the negative third, which will give us a stress here of 15.1 KSI. And then our average pre-stressing is going to be our modulus in our pre-stressing times our strain in the column plus our locked-in strain differential, which we found to be 6.27 times 10 to the negative third. So we'll find then our FP to be equal to 193.5 KSI. So now we have the stress in our concrete, in our steel, and in our pre-stressing. We can next find the axial force in the column by using our equilibrium expression. N is our unknown, so we'll have N equal to the area of our concrete, 318.8 square inches, times our stress in our concrete, 0.206 KSI, plus the area of our non-pre-stressed reinforcement, 4 square inches, times our stress in the non-pre-stressed reinforcement, 15.1 KSI, and then plus the area of our pre-stressed reinforcement, 1.224 square inches, times our stress, 193.5 KSI. This will give us an axial load here, N equal to 363.9 kips. The next part of the problem, we can find our local stresses caused by the imposed displacement. We can start with our equilibrium expression, and we're going to define a new term. This delta epsilon C cracking is the incremental strain at the crack. There's going to be additional strain in the steel and pre-stressing because at a crack, the stress in our concrete is going to be equal to 0. So let's plug in all of our known values. So the local stresses caused by the imposed displacement, we can use our equilibrium expression, and we'll have N equal to, so 0 because we're getting rid of that first term there. So then we'll just have our steel, 4 square inches, times the modulus of our steel, 29,000 KSI times the initial strain, 0.5, or the strain at this point, 0.52 times 10 to the negative third, plus this additional incremental strain at the crack. And then we can add in the same term here for our pre-stressing. So we'll have 1.224 square inches, the total area of pre-stressing, 28,500 KSI, the stiffness of our pre-stressing, and then we need to add, so 0.52 times 10 to the negative third plus 6.27 times 10 to the negative third plus this incremental strain again. So solving this for the incremental strain, we'll get, we'll set this equal to our axial load at this point, so 363.9 kips. We can then solve this equation for our incremental strain here, and we'll get delta epsilon C crack. So I have that wrong, but delta epsilon C crack equal to 0.442 times 10 to the negative third. This is the additional strain that's going to happen in the steel and pre-stressing at the location of a crack. We can now use that delta epsilon C crack to figure out the stress in the steel and the stress in the pre-stressing. We'll start with the stress in the steel. So the stress in the steel will be equal to our modulus of our steel, 29,000 KSI, times our average strain in the column, 0.52 times 10 to the negative third, plus this additional strain at the crack, 0.442 times 10 to the negative third. And solving this, we'll get a stress of 27.9 KSI. We can see this value is less than the yield stress of our steel, so we're okay here. If we were to find that at a crack, our steel stress was greater than our yield stress, then we would need to kind of go back and modify our assumptions, because we can't have a stress greater than our yield stress. So we would have less axial load in our column at this point. But we can continue now. In the pre-stressing at a crack, we'll have equal to 28,500 times the average strain in the column, 0.52 times 10 to the negative third, plus our locked-in strain, 6.27 times 10 to the negative third, plus this additional strain at a crack, 0.442 times 10 to the negative third. And this will give us a stress equal to 206.1 KSI. So again, this value is less than the yield stress in our pre-stressing, which is typically around 243 KSI. So we're okay here as well. All right, next we need to find our forces, and we can just do that by taking our stress times our area. So in the steel, we had 4 square inches of non-pre-stressed steel times 27.9 KSI. Will give us a force of 111.6 kips. And in our pre-stressing, we had a total area of 1.224 square inches times the stress, 206.1, which will give us a value here of 252.3 kips. If we add this 111.6 to our 253, or 252.3 kips, we'll get it equal to 363.9 kips. And if you look back, you can see that this force is equal to the average force in the column, including tension, stiffening, and our concrete component. So that checks. You want to make sure that your total force at the crack is equal to the total force in the average total force in the column. The last check that I mentioned, so above we were checking to make sure that we had stress in the non-pre-stressed steel and stress in the pre-stressed steel less than the yield stresses. So we can also check that by looking at the total capacity at a crack, assuming that we have yield in both the non-pre-stressed and pre-stressed steel. And you can see that this 363.9 is less than 537.4, so we know that we're okay here. If we had a value above that again, we would need to cap the total force in the column at 537.4. So what that means is we couldn't take advantage of tension stiffening as much as we had. We would need to decrease the stress in our concrete in the average response. But I talk about this a little more in the full lecture on this module. So that concludes this example problem.